Hello everyone, welcome back. So in this video we will do an experiment and we'll measure the diameter of a given wire and we'll also measure the diameter of a given spherical ball. This is a steel ball, very small steel ball. So we will measure its diameter. Once we measure the diameter of this steel ball, we can find out the volume of this steel ball also. So these are very the diameter of the wire also very small. So to measure this type of small diameter, we'll use one apparatus, that is screw gauge. So this is a screw gauge. First I'll explain the how we can calculate the zero error, the least count, and how we'll make the observation table. All these things we will discuss. Then I'll explain how we can take the measurement, how we will measure the diameter of this wire and also diameter of this spherical ball. So let us go to the um, observation table first. Before that, let me show you what is a zero error. So zero error, if the apparatus, you can see this apparatus, right? So so now this is a closure view. I'm showing you here. You can see this is a screw gauge and two scales are there basically. You can see one circular scale where it is 0, 10, 20, 30 like that up to 100. This is a circular scale, and if I am rotating it and opening it up, you can see there is a scale inside, right? There is a scale inside, and there is it's also, you can see 10 divisions are there. So it's a centimeter scale, so one division is 1 millimeter. Now how will you calculate the least count of the apparatus? That is the first thing you have to do when you will start the experiment. So first, to calculate the least count, we have to calculate the pitch of this apparatus first, and before that also you have to check if any zero error is there or not. Now you see this is your reference zero line of the main scale, or there is, and this is the zero on the circular scale. If they are matching, right, this is the, you can see this is the main scale zero is exactly when we will tight both the jaw. If it is matching exactly, then there is no zero error. I will show you another apparatus where there is some zero error is there. First we will calculate zero error. So here you will see that when I am tightening and both jaw are coinciding, they are tight completely, you will see that the zero, here is the reference line. Yeah, this is the reference line, and the reference line is touching at 40, right? So it's not exactly coinciding with the zero of the circular scale. So it's you can say it is having some zero error. Then if it is positive zero error or negative zero error, how do you know? If the error is coming, if it is ahead of the starting point of main scale, then it is positive zero error. If it is coming to the left side, then it will have the negative zero error. Fine. So this is having a you can say positive zero error and positive zero error of 40, right? 45 is coinciding with this one. So we'll first calculate the positive zero error and negative zero error. So how will you calculate? I'll just show you. So the positive zero error you will calculate using the formula. You will use this formula for positive zero error. You see, for positive zero error, your formula is positive zero error and we are doing For this one is screw gauge. We are doing the experiment for screw gauge. So positive zero error, how will you calculate? Positive zero error is the coincidence, circular coincidence. Suppose for example for this apparatus 45, the circular coincidence is 45, right? So you will write circular coincidence, that will be your, let's say 45 for my apparatus. Then we'll multiply least count with it. Whatever least count will get, that will give you the positive zero error. So if you are having a positive zero error, whatever the result you will get, let's say the diameter of this steel ball, whatever the result you will get, you will subtract it, because positive zero error, that means this much extra you are getting. So whatever the result minus positive your zero error, positive zero error, you will subtract it, right? You will subtract the positive zero error. Now if a negative zero error, so how will you calculate? You will multiply your circular coincidence with the least count. Now if there is negative zero error, if there is negative zero error, then what you will do? You will subtract 100 minus the number coincidence, right? CC I am writing, circular coincidence, whole into LC. You will multiply with LC, you will get a negative zero error. Now if negative zero error is there, this is the result. With the result, what you will do? You will add negative zero error. You will add negative zero error. So this is what you will do with the, first you will check with your apparatus that whether it is having positive zero error or negative zero error. Then we will start calculating the least count. So what you will do? Just you keep start from the, let's say 0 mark. So you will rotate, let's say it starts from 80, right? It starts from 80, so you will rotate it. First you tight both the jaw, then you will rotate it, starts from 80, again 80 will come, that means one rotation. For one rotation you can see 1 millimeter is, or 0.1 centimeter is visible in my main scale. So first I will calculate the pitch. So how will you calculate pitch? So my pitch of this apparatus is the distance traveled in the main scale, the distance, or that is called pitch scale, distance traveled in main scale divided by your number of complete rotation, number of complete rotation. So I rotated once, complete one rotation. For one main scale it is traveling 0.1 centimeter. So my pitch for this apparatus will be 0.1 divided by 1, that is 0.1 centimeter. Now see, if you are having two rotation to get 0.1 centimeter, so we will write 0.1 divided by 2. Accordingly you will calculate. So your pitch will change according to your apparatus, given apparatus. So you take it, first you calculate it carefully, pitch, then you will calculate least count, which is most important. So least count is pitch by number of circular division, number of circular division. So pitch we got, and number of circular division, in my apparatus 100 divisions are there. You can see 100 divisions are there. You can see 80, 90 and 100 divisions are there. Some of the apparatus there may be 50 divisions, so you take it accordingly. You calculate according to your apparatus the least count. So here my pitch is 0.1 divided by number of circular division is let's say 100, so I'll get 0.001 centimeter is my least count. So once I'm done with my least count and zero error, because zero error I'll check, then I'll go to the observation table. So how will I make observation table? To calculate the diameter, so I'll take my main scale reading, or that is pitch scale reading also, then I'll write circular coincidence, then I'll write LC, then I'll multiply LC into CC, then I'll add this with this is my main scale, this is my LC into CC. Let's say this is 1, this is 2, this is 3, this is 4, so I'll add 1 plus 4. This will be my total diameter, right? So basically this LC into CC will give you the extra. That means suppose I'm measuring this one, the steel ball, I'll keep the steel ball, my sample I'll keep in between the two jaws, upper jaw and lower jaw. I'll tight it, right? Once I tight, I'll do the again here at the end, so that completely it's tight now, right? So you can see my reading is 5.1, sorry, 0.6 it is. So 0.6 centimeter, but it is not exactly 0.6 centimeter, it's slightly ahead of 0.6, it is just in between 0.6 and 0.7. so my MSR, I'll take 10 times reading, so my MSR will be almost all the time it will be 0.6 always, but my LC into CC, that will change, and LC into CC is giving you what? Now it is in between 0.6 and 0.7, so where exactly it is 0.62 or 0.63 or 0.64, means it's not 0.7, it's 0.6, but it may be 0.65, 0.63. so what is the extra? That is giving my LC into CC. So and that extra plus this main scale will give you something like 0.63 or 64, whatever you will get, right? So this is your total diameter of this will give me the total diameter, and so this is my 0.6 centimeter is the diameter, and this one then I'll mark the which line is circular, which line is coinciding with the main scale. Let's say 65 is coinciding here, so I'll write 65. Then LC we have already calculated 0.0001, and I'll multiply with 65, so it will become I'll multiply, so it will become 0.065. so when I'll add it with 0.6, it will become 0.665 centimeter. So I got this one like this. I'll get different circular coincidence. I'll open it up again, I'll tight it, right? I'll again tight it, and I'll again note the CC. Obviously same main scale reading will come in all the cases mostly, and I'll get a difference CC. Then I'll find out the total. Whatever the total I'll get, I'll divide by 10. Suppose I'm taking 10 observations, right? 1 to 10 I'm taking 10 observation, 1 2 3 like that 10 observation. So I'll divide by 10 and I'll get the average diameter. Now once I get the diameter, my M is to find out the volume of this one. So what I'll do, I'll calculate my volume. So volume formula, it's a sphere, so volume will become 4 by 3 pi RQ. Here we calculated diameter, so we can write that your radius will become 4 by 3 pi. In terms of diameter, I can write d by 2 whole cube, or this will become 4 by 3 8 pi d cube, right? So d you can put here, and if you have and you can calculate the volume. And if your d is having some errors, so with the average diameter, if it is a positive error, you subtract the error. If it is a negative error, you add the negative error. If you have a positive error, you subtract the positive error from the diameter, so you will get the your desired result. Once you get the result, you can find out the volume. Then finally you can calculate the error. Error can be different due to your observation, due to instrument, maybe different. So how do you calculate error? We know the formula, that relative error delta v by v equal to, these are the constants, so it will be 3 delta d by d. So this will be relative error, right? And percentage error you can calculate. Just you will multiply 100, whatever the result you will calculate, you will multiply 100 with it, then you will get the percentage error. So finally you will write the result, right? The result you will write that we found, or I found, the diameter, the volume of the spherical ball is whatever you got, with 8%, whatever the percentage error you will get, you will write that percentage of error. This is your result, and discussion you can write, and the sources of error later you can write. So what is this delta d you will use? Delta d is basically this fluctuations, whatever you are getting, LC into CC. This is the average one. You can find out this is the error you are getting, because MSR is the constant, there is no error you are getting. So you can, this one you can is visible to you clearly. So the fluctuation you are getting with LC into CC, or basically CC, so you can average out and you can use this delta d here, right? So this is the change in diameter, delta d you are getting, and d is fixed, you can add it and average out. So d you can write, this is the, or you can average out this one. This one is the diameter, right? So out of this one you are having the error, this one, so you can average out this one. So this is your diameter and this is your error. So error by diameter will give you the relative error 3, you multiply, because the formula, right? You know this type of formula, and then you will calculate the percentage error. So this way you can calculate the volume of a spherical ball. Similarly you can measure in a simple way, just diameter per diameter. You also will follow the same procedure. Diameter of a wire, you will tight it, the same table you will make, main scale reading, whatever the result, 0.1 let's say. Then circular coincidence you will write, then LC into CC, you will add it, average out, and you will find out the result diameter. The same procedure you will follow. In the term 1, in the syllabus it is also asked to calculate thickness of a given sample. So if a coin or some steel or any object will be given whose thickness you are supposed to measure, you can also measure the thickness of a wire, thickness of a sample. So same procedure you will follow, and you can calculate the thickness of the given sample. Thank you for watching the video. In the next video I'll do another experiment. Thank you.